Yeah, comments, questions, concerns, anything I gave you from Friday. It was a selection of work energy theorem and then energy conservation. I gave you 1 to 4 and then 6, 10, and 11 off of page 165, 166. And then I gave you 1, 3, 4 AC, 8, and 9, page 172, 173. Anything anyone wants me to go over?
Oh, does it matter if we oh no.
Sorry?
The first one that I was looking at it, like what speed energy or if you like
Okay. Yeah, I mean, effectively, it amounts to the same thing. But typically, I'll get you to write it like that. I mean, as work. But yeah, are there any other, like, nothing? Going once, twice, 3 times, sold. Okay, cool. Find this page. This, I have it on reasonably good authority, is totally brand new. Okay, so momentum, similar to energy, is one of those unmeasurable concepts. It's measurable, but it's not measurable. I know that doesn't really tell you anything. Momentum, what is it? What is your current experience with this concept? We've heard of this word before? Momentum, where have we heard it, Nathan? You don't know where you've heard it, but you've just heard it. Where have you heard it? Moving objects, especially fast ones, we tend to say have lots of momentum. Or heavy ones. Okay? You've actually heard it in that context? Okay. Momentum also gets used in the context of sports all the time. The idea that once a team is on the roll, it's that momentum is building, whatever that means. It's not like anything is really changing with the team, but like the Colorado Avalanche last night in one of the most dominant playoff performances I've ever seen. It's this thing, once you've got it and you continue to develop it, it tends to build. What happened in the game? It was 7-7. They pounded the Vegas Knights 7-1. It was 6-0 halfway through the third. And then they got a 9-minute power play. It was awesome. Reeves got ejected, and I can't stand him. So it was a great game. Great game. The only game that could be better is if the Canadians beat the Leafs tonight. That'd be amazing. Okay, anyway. So Joseph, you said 2 things. You said, in the context of momentum, in the physics context, we typically say that fast-moving objects have momentum. The fast-moving or heavy-moving objects have momentum. Is typically what we associate with this concept. We'll talk about what impulse is in a second here. But yeah, typically what momentum means in a physical concept, as a physical concept, is the amount of motion that an object has. That amount of motion, as Joseph has already said, is dictated by 2 things: the size of your object and the speed at which the object's moving. You can think of the amount of motion that an object has as being a measurement of how difficult would it be for me to stop this object. If it is easy for you to stop the object, it doesn't have a lot of momentum. If it's difficult for you to stop the object, it's going to have a lot of momentum. Like a rolling car. I don't know if anyone's ever tried to stop a rolling car. It's not impossible, but it's certainly difficult. Even if it's not moving very fast, a slight incline, you put the car in neutral, and it's going to start rolling at you. It's more likely that it's going to start pushing you slowly down that same incline. It's not moving very fast, but cars are typically fairly heavy. Unless there's the smart cars, and then there's your Yaris. But your average car, even not moving very quickly, is going to have, it would be this example here. Heavy object moving really slowly is going to have a large amount of motion in that it becomes very difficult to stop. Somewhat equivalently, if you've got a small object moving at you very, very quickly, I mean, these are typically easier to stop, but the trade-off is generally a significant amount of pain. Like a bullet or a baseball, or well, those are the two. So like if you're standing at the plate and the pitcher decides to throw it at you, yeah, you're going to stop it, but it's going to hurt a fair bit. It's going to take a fair bit out of you to stop that object. A bullet is another one. It takes a fair bit. I mean, there's a reason why body armor is as thick and heavy as it is, because if you're going to try and stop a bullet, you need something substantial to absorb the kinetic energy that's there. So even a small object moving very, very quickly has a large amount of momentum. The concept here that we are discussing is this idea of inertia. And inertia is the tendency for an object to remain in motion. Or, yeah, I'll say in its motion, whatever its motion is. So momentum is this combination of concepts, the speed and the mass of your object. So we say momentum is proportional to both of those things, giving us this formula here. Since momentum depends on both mass and speed, we call it a motion product, which is why momentum is given the letter P. It is a product of the mass of an object and the velocity of an object. Because velocity is a vector and you're multiplying it by a scalar, momentum itself is also a vector. So things typically have, well, not typically, things do have momentum in a particular direction. And it's the direction that you're moving it in. The units, we can take a look at what those are. The units of momentum, mass is kilograms, velocity is meter per second. So we typically say that the units of momentum are kilogram meters per second. There is an alternative unit for this, though, as well. The alternative unit is what's called the Newton second, which is an interesting concept. If we take this kilogram meters per second, the idea of kilogram meters per second, and we multiply it by, so if I take my kilogram meters per second, and I use that technique that we looked at before, multiplying it by 1, the 1 in this case is going to be seconds over seconds. What I'm going to get here is kilogram meters per second squared times seconds. And this thing here is a mass times an acceleration. That's just a force. So because this is a force, we can write it as a Newton. So we get this idea that momentum can also be measured in Newton seconds, which is going to give us the next formulation here. So we've got momentum, P equals mv, kilogram meters per second. But we've also got this idea that momentum, P, is equal to a force times a time. My newtons times my seconds. So we'll flip the page. We'll talk about this briefly, I guess. You know what? No, I'm just gonna skip all this. I'm not gonna show you the. Well, I mean, I guess whatever. I'm not gonna show you the proof, but I'm gonna talk about this with example 3 is talking about here. The idea that momentum change equals mass times a change in velocity. So if I got something that looks like this, typically we're less concerned about momentum and more concerned about the change in momentum or how we're going to go about doing that. So if I'm concerning myself with a change in momentum, that's just going to be my momentum final minus my momentum initial. Momentum final is just mv final minus mv initial. Typically your mass isn't going to change. So if I factor out my mass, I guess I am doing the proof for you here. That's just going to be v final minus v initial. So your change in momentum is just your mass times your change in velocity. Typically, at this stage, that's the kind of stuff that we're going to look at here. If you go on in physics, you'll talk about things like, okay, well, the rocket, as it flies, is going to start to burn up fuel. As it uses fuel, it's becoming lighter. So how is momentum changing as the rocket, flies through the air and uses up its fuel, becoming faster while at the same time becoming less heavy? You can talk. You'll look at stuff like that. But for the stuff that we are dealing with here, the idea that change in momentum is the mass times the change in velocity is what we're going to use here. So flip the page. There's another concept related to momentum called impulse that we're going to look at here. So we've already established that momentum can be equal to a force times a time. And the way that this actually gets formulated is not that just momentum is equal to a force times a time. Because as you apply a force, you're giving an object an acceleration. As you're accelerating an object, you're changing its velocity. So it's not just momentum that's equal to a force times a time. What we actually are going to concern ourselves here is with a change in momentum being equal to a force times a time. So as you apply a force for a particular length of time, you're changing the momentum of an object, which should be relatively straightforward. This concept here, the idea that mass times the change in velocity being equal to a force times a time, this is impulse. And as far as impulse is concerned, if you were asked to find the impulse, any one of these, either side of this equation, will work to satisfy finding what the impulse is.
Because on the formula.
Yeah, t. It's elapsed time, which is change in time. Yeah, I'm getting sloppy with my notation. You are right. Is the impulse equation on the formula sheet? Where is it? Yeah, there it is. Yeah, so now we're dealing with these guys down here. This is momentum. Momentum and impulse are here.
This seems like a short extent of change.
They are.
Oh.
T and delta t? Is that what you mean? Or
Momentum and impulse, they seem like
no, well, momentum is what is your, momentum is an instantaneous thing. So what is your momentum right now versus how does your momentum change over the course of a situation? Impulse is that change in momentum. Momentum itself is right now. What do you got? Okay. So, and as far as t or delta t, yeah, sure. I can rewrite this. M delta v equals f delta t. Those are, when we're dealing with time, we're concerned with the passage of time, and sure, I can get more consistent with my notation. Because it's Monday morning and I'm sloppy. Okay, so impulse is you can think of impulse as the equivalent to an acceleration, where a change in a velocity, like you accelerate something so the velocity changes, a force over a time changes the momentum of an object. Those are conceptually very, very similar. So let's do an example like that. We've got a 125 gram baseball moving east. 125 gram baseball moving east at 150 kilometers per hour. It's hit by a baseball bat. Typically, that's what happens to baseballs. The ball is on the bat for this length of time, 0.075 seconds, and leaves the bat moving west at 92 kilometers per hour. You want to find the net force and the direction on the ball. So at this stage, if I gave you this problem, without talking about momentum, how would you solve this problem? What concepts could you use that we've already looked at to deal with this?
Probably find the acceleration.
Okay, so we could use kinematics to find acceleration. And then what do you do? What would you do then, Ashton?
That is a good question.
Well, okay, look what it's asking for. It's asking for the net force. You've used the kinematics to find the acceleration. To find a force from an acceleration, you just. And dynamics. You know what? I can appreciate that. Okay? So up until this point, this problem could be solved that way relatively easily. But we can also use this formulation that we've got here. So let's go through and do it. We're going to draw the problem first. We've got a ball heading east. The mass of our ball is 125 grams, so I'm going to convert that to kilograms right away. 0.125 kilograms. We know that this thing has an initial velocity of 150 kilometers per hour. So we're going to convert that right away to meters per second. What's 150 kilometers per hour in meters per second? Okay, yeah, divide that by 3.6. Okay, so I'm just going to round it to 41.67 then. Do you remember this conversion, or is this something we should toss on our formula sheet?
I tossed it on my phone.
Okay, let's toss it on our formula sheet. I'll put it over here on the side. Kilometers per hour, meters per second. To go from kilometers per hour to meters per second, you're dividing by 3.6. To go from meters per second and kilometers per hour, multiplying by 3.6. It's a useful conversion to have. So we've got the initial velocity, we've got the mass of our ball. We are told that eventually the ball is going to meet a bat. There's the bat. The ball is going to hit the bat. And it's going to rebound that way. The mass of our ball isn't changing, but now it's got a new velocity. V final is 92 kilometers per hour, but it's going the other way. Velocity is a vector, so what do we have to do with our velocity? It's going to be negative 92 kilometers per hour. So let's convert that right away to how many meters per second? 25.56 meters per second. The idea that it's going the other way means that we have to take into account this negative here is something that may have impacted you guys adversely on your first test. So let's take a look at this. We want to find the net force in the direction of the ball, and instead of using kinematics and dynamics, we're going to use the impulse equation here. So we're going to use the idea that my force times my change in time is going to equal my mass times my change in velocity. So my change in time is that 0.075 seconds that the ball is actually in contact with the bat. The mass of the ball we've got, or that's going to equal the mass of the ball, 0.125. And then a change in velocity is a final velocity minus an initial velocity. My final velocity is negative 25.56 meters per second. Minus, yes, bless you, my initial velocity of 41.67 meters per second. So we can find out that the force is equal to what? Which means what? The ball's going fast the other way. Yeah, the force, I mean, and that makes sense, right? The force has to be to the left because my ball was moving to the right. Now the ball's moving to the left. So my force, well, it's not even left and right, it's east and west, is going to be 112.05 newtons west. That is the force required to change the direction of the ball from 150 kilometers per hour east to 92 kilometers per hour west. That's the impulse equation. Comments, questions, concerns? Relatively straightforward, yes? Momentum is not an overly difficult concept. Flip the page. The applications, though, are interesting. We could have solved the previous equation using impulse. We used impulse. We could have used it, solved it using Newton's second law, as Ashton already said. We could have found the acceleration using kinematics. That we could have found F net equals ma using dynamics. So why bother with this idea of impulse? The reason that momentum and impulse is useful to analyze things is because of this style of situation here, collision problems. Typically when things collide, they collide a bunch of different ways. Either one object bounces off another, or they crumple together. And when you're looking at things crumpling together, all of a sudden using kinematics and dynamics becomes really difficult to analyze what's actually going on here. Using momentum allows us to take into account that objects are going to shrink potentially if things are exploding, or grow if things are crumpling together. The idea, if you think about an offensive lineman, excuse my ignorance of football, but you've got an offensive lineman. No, that's not what I want. Who tackles quarterbacks? Give me the player, football players. Yeah, linebacker? Okay. You got a linebacker tackling a quarterback. The idea that they were moving separately, and now they're sliding together as one pummels the other. Analyzing that using dynamics and kinematics is much more difficult than using momentum, which is why even though it's so similar, that's why we use it. An application of momentum is the classic egg drop. How many of you guys have done this with Mr. Harvey back in Science 10? Or just in general? Hans, have you ever done an egg drop in general? The goal of the egg drop is to do what? Keep the egg, drop the egg, but have it remain intact. What's the strategy? What are you ultimately trying to do? You're trying to make the egg so it doesn't crack. But what are you trying to do, actually? You want to cushion the egg as the velocity decreases. The velocity is going to decrease anyway. I just throw it off the rotunda. It's going to decrease. very rapidly at the bottom, and that's what's going to crack the egg. What you're trying to do is you're trying to increase the amount of time that change in velocity occurs, which is an interesting idea. We've got a change in time, a force, a mass, and a change in velocity. So you've got, effectively, this is an application of this concept of impulse. If these two concepts are equivalent, the mass of my egg isn't going to change. The changing of my velocity isn't going to change either. It has an impact velocity, and it's going down to 0. That's remaining constant. So I've got a force times a change in time equals some constant value. If my change in time is really small, the value for my force has to be really big. But if I can increase my time, what's that going to do to my force? Right. I've got two things multiplied together. If I can decrease our time, I'll say it this way. A decrease in time leads to an increase in force. But if I can increase my change in time, making it so that the change in the velocity happens over a larger span, that's going to lead to a decreased force. So we do this in an egg drop. Where is a way more relevant application of this occur? Like a car crash. What part of a car crash?
Like if you collide with a wall or a tree or any object, pretty much, you want to have as little force as possible so you don't get decapitated or die. Or something like
So
that.
what objects are designed? You're right. If you're driving in the car and this is you and a steel box and you're going and that steel box hits a brick wall, you're shortly thereafter going to hit the brick wall. It's going to be problematic for you. So what exists now in cars to airbags one?
Metal frame.
The seatbelt is the other. And then, or the crumple zone on the car.
Yeah.
The crumple zone on the car decreases the amount of time that the car takes to come to a stop. The car is still going to come to a stop pretty quickly. But if we can give you a pillow instantly out of nowhere to cushion your head as it kind of gently comes to a rest. Sorry? Just no. Just no. Okay? This is the concept, right? The reason airbags exist is because we recognize that to increase the time it takes you to stop decreases the force on your body. Before airbags were a thing, the steering wheel stopped you. It's pretty rigid, stops you pretty quickly. The giant exploding marshmallow that comes at you and then kind of pushes your head down is designed to increase the time that your head is stopping, which is decreasing the force on your head. And we can look at this practically. We can just look at some values here using these two examples here. So our force is, I'll isolate this for the force already. I got my force is going to be equal to m delta v over delta t. What does an egg weigh? A kilogram? Okay, we have a kilogram egg. Okay, so let's assume our egg weighs a kilogram. How fast is our velocity, or how fast is our object, our egg, going to hit the ground? 8 meters per second. Okay. Yes. At this point, it's an analysis. I don't care. We want it's going to hit the ground at 8 meters per second. If it's just going to hit the ground and come to a stop basically immediately, the amount of time there is going to be very, very small. That's like, I don't know, 0.01 seconds. No, we're not doing that. Okay, so let's 8 divided by 0.1, or 0.01 rather. 800 newtons. Okay? That is a substantial force on our little egg. Well, it's not a very little egg, it's a kilogram. But, whatever. Our ostrich egg. Conversely, in this situation here, the egg is going to hit the water, and then this this time is going to be much, much larger. How long is it going to take that egg to hit the ground? The bottom of the cup. It's not going to be 2 minutes.
That's a long cup. It's only 2 seconds.
2 seconds. Even if it's not 2 seconds, even if it's, let's say, even if it's a second, even if it's a half a second. If my delta t is half a second, let's run it again. F equals m delta v over delta t. My mass is a kilogram. The speed at which it hits the surface of the water is 8. If my time extends to even half a second, 8 divided by 0.5 is what? 16. Okay? In the grand scheme of lengths of time, a tenth of a or a hundredth of a second and half a second are still incredibly quick as far as how you're able to perceive things. But the change in force is dramatic. Okay? 800 newtons down to 16 newtons. That's a 50 times difference in the amount of force required to stop that egg.
So you're saying we should put water in the cars.
No, water's actually bad. Water's bad because water's non-compressible, which means hitting water that fast is actually going to be like hitting a concrete wall itself. So no, water's not the thing to do. But in the case of the egg, if the egg's even a little bit aerodynamic, it'll slide in there like a diver. It's the difference between a belly flop versus a dive. Flip the page.
We're not talking about it.
Okay. So we're going to look at it graphically as well. This idea of impulse and momentum. If we look at a force versus time graph for the egg hitting the floor, it's going to look like this. We've got a very short period of time. This is our 0.01 seconds. This is our maximum force. There are two things that we can do with every graph. We can find the slope, we can find the area. Slope on this thing is not going to be super useful, so let's look at the area. The area of that triangle is going to be 1/2 base times height, which is going to be 1/2 the time times the force. Oh look, force times time, that means we're looking at the area under a force time graph is impulse. Now all of a sudden this thing is graphically useful. So now that we've got this idea that the area underneath the force time graph, so those of you who are in calculus, if you're going to take the integral of your force function with respect to time, that's going to give you this impulse. Now Ashton, you're right, we can start applying calculus to this. We're not going to. We can use these graphs to analyze the previous situation. Which combination of graphs, A, B, or C, is the best way to analyze our two situations with the egg? Why? Who said C? Like, was that you or Zach? That was you. There's two of you. Why did the two of you say C? So why not B? Okay, we're cool with it not being A, yeah? Oh.
Good morning, Jeff.
Okay, so why not B?
Double, like the length of time has over double, but you've only half your force. Which seems
The length of time is more than double, but we've only halved our force. So these two areas if I flip back really quickly here, we said that F delta T My mass of my object doesn't change. My change in velocity doesn't change. So these things have to remain constant. Which means that these two areas need to remain the same. So in these two graphs, my impulses are not equal. Over here they would be. You're not bad at analyzing graphs, Ashton. You just haven't done a lot of it. You're just out of practice of analyzing graphs. So it can't be B. It's got to be C. Or if you want to analyze it the way Zach and Blake did it, I mean, there are no values present there either, but the idea that I only halved my force, but I more than doubled my time. They need to be, the change needs to be proportional. Okay, that's the other way to look at it too. Changes in F and T need to be proportional. So if you double one, you have the other, and vice versa. This is your introduction to momentum. Let's get you guys doing stuff with it. Yeah, that's it.
Good morning.
So back to this, I guess. Yeah, it is an awkward transition for sure. So this is what I want you working on. As Mr. Cookson said, should you desire to talk to anyone, let me know. You can, yeah, do what you got to do. There's not a lot here. 2 to 5 is 4 questions, and 12 is a 5th question. So we'll see where you guys are at 10 o'clock, and then we'll look at the application of momentum into colliding objects.